Hi guys, we have one important topic from last night's lesson that we need to finish up, and then a few bits and pieces, a couple other problems that we skipped over, and then I also want to look at some verify the identity problems just to get as much practice with those problems as we can. The thing that we didn't get to, the big idea that we didn't get to, it's not a big idea, it's more of a special kind of problem that we haven't seen before, is using our calculators to solve some equations. So this first problem says approximate to the nearest 0.1 degrees all angles in the interval 0 to 360 that satisfy the equation. So we have sine of theta is equal to 0.8225. So first off, let's look at the graph. Let's look at the graph of sine theta, I guess. Let's just look at the graph of y equals sine x on the interval 0. Well, let's just call it 0 to 360 degrees. By the way, we're going to be talking more about graphs next week. We have a whole section on graphs, and so all that stuff I said last night about remembering some graph transformation stuff, that's what we're going to be talking about next week. Anyway, sine, let's see, it starts here and then goes up to 1 and then back down and then down to -1 and then back up. So my graph on 0 to 360 looks something like this. And then if we want to figure out, we want to solve this equation, we can draw a line, the line y equals 0.8225, and we can see that there are going to be two solutions. There's going to be one between 0 and 90 degrees and one between 90 and 180 degrees. All right. Now, we're going to need to use our calculator to do this, and we're going to spend some time much later on in the semester. I don't know, much later is maybe strong, but we're going to wait a month or two and then come back to this business of inverse trig functions. So what we're going to do is there's going to be a special theta. I'm going to call it theta sub 0. So the notation is going to be a little bit obnoxious here. There's a theta sub 0 value that we're going to get by using our calculator. And this is sine inverse. We're going to take the sine inverse function. You learned about inverse functions in your algebra class. This is an inverse. It's a little bit confusing when you first learn about it. And it's probably one of the more confusing things in trig. But for right now, we just have to push buttons on the calculator and understand what our calculator is doing. That's our goal today, is to understand what our calculator is telling us. All right? We're going to do sine inverse of 0.8225. All right? On the calculator, it looks like the sine inverse, regardless of what your calculator looks like, the sine inverse is usually hiding behind the sine button. It's a second function button. So I want to hit my second function button and the sine button, and it spits out the sine inverse, and then I'll type in my number, 0.8225, and then hit the enter button, and the calculator spits out 55.33, yada, yada, yada. Notice now that my calculator's in degree mode, which we want. We want an angle in degrees, so my calculator's in degree mode. So let's see, to the nearest tenth of a degree, this angle is about 55.3 degrees. And that's this one. That's this angle right here. We need to figure out how to get this angle, this second one. And the act of finding that second one is a little bit challenging, and this is where we're going to need reference angles. So now let's go look at our unit circle now. Let's go look at our unit circle. Well, we found the first angle is 55. Here's our theta sub 0 here. The number that the calculator spit out turned out to be one of our answers. It's not always going to be, but it turned out to be one of our answers. There's a second angle here in the second quadrant. That's going to be, let's see, how do I draw that in here? I guess I should use my colored. There's a second one here. I'm going to call it theta 2. And the interesting thing about theta 2 is it has the same reference angle as my other solution. All right? It has the same reference angle as my other solution. Now, in this case, if I take this angle that I'm looking for here, theta 2, and I don't want to do that. If in this particular case, if I add my reference angle, which also happens to be theta sub 0 in this case, there's, by the way, guys, in some of these problems are going to end up being 4 different angles. That's why I'm labeling them the way that I am. Okay. If I take these two angles and add them together, then I get 180 degrees. So if I want to find this other angle, theta sub 2, that's going to be 180 degrees minus this theta sub 0 angle that I found. All right, so that ends up being about 180 degrees minus 55.3 degrees, which I guess I actually need I can do that. I got a calculator right on my screen. What's wrong with me? 180 minus 55.3. Or honestly, I could just hit the last answer button. That'd have been a smarter thing. Anyways, this angle is 24.7 degrees. Sorry, 124.7 degrees. All right, now, understanding what our calculator gives us, if I plug a value into this sine inverse function, it says right in your notes that sine inverse x gives the angle in, depending on if you're in degree mode or radian mode, in degree mode, oops, that's wrong, gives the angle in the interval minus 90 degrees to 90 degrees, or in radian mode, minus pi over 2 to pi over 2, with, I guess, the angle theta, with sine of theta equal to x. Okay, so it produces one specific angle. Now, remember, all these trig functions are periodic, and there are infinitely many solutions to any trig equation. And so there doesn't have a, if you remember learning about inverse functions in your algebra class, you need a one-to-one function in order for there to be an inverse, and the trig functions are highly not one-to-one. Okay? So the inverse trig function on your calculator, and when we learn more about inverse trig functions in general, they have to produce a specific answer. And for the sine function, we're going to pick the answer in one of these two intervals, depending on if we're in degrees or radians. Now, you're not meant to understand why it does one of these intervals, and I would encourage you not to worry about that right now. We'll answer that question later on in the course. All right, right now, the goal is to understand the answer that your calculator is using, and then the secondary goal is to be able to use that answer, the number that your calculator produces, in order to find the answers to the question. And that requires us to understand what the answers look like via this graph. Okay, Here I knew that there was one answer in the first quadrant and one answer in the second quadrant. Use what we know about reference angles and the unit circle to come up with a game plan for finding the right angles. And then again, understand the answer produced by the calculator so that we could get the problem done. All right, let's look at another one. We have tangent of theta is 1.5214. If I look at the graph of tangent on the interval 0 to 2 pi, or at least the graph of y equals tangent x, there is an asymptote at pi over 2. And we have pi. There is another asymptote at 3 pi over 2. And then here's 2 pi. The graph of y equals tangent of x on this interval looks basically like this. There we go. And if I go up to y equals 1.5214, we can again see that there are two solutions. Looks like there's one in the first quadrant and one in the second quadrant. Sorry, we're doing these things in degrees, so this should be 90 degrees and 180 degrees and 270 degrees and 360 degrees. So I have one answer that's between 0 and 90 and one answer that's between 180 and 270. Now if I do the inverse tangent function, so again I'm going to call this the value produced by the inverse tangent function theta sub 0. That would be the inverse tangent of 1.5214. And on the calculator, so in order to get inverse tangent, it's hiding behind the tangent button, so I got to hit second function tangent. 1.5214 gives me an angle rounded to the nearest tenth of about 56.7 degrees. All right, so that's actually the first answer. Actually, I meant to call this theta sub 1 in the last example. The answer produced by the calculator, that's what I'm calling theta sub 0, also happens to be one of the numbers that I'm looking for. One of the solutions here. In order to find the other solution, let's think about, once again, our unit circle. We have theta sub 1 in this first quadrant. That's one of the angles. The other angle is going to be a comparable angle in the third quadrant. I go all the way around to that angle in the third quadrant, and it's going to have a reference angle that's the same as theta sub 0 in this case, which is the same as theta sub 1. I guess there's also a reference angle. Like I told you guys, there's going to be 4 angles sometimes. In this particular problem, 3 of those angles happen to be the same angle. Okay? But anyways, I guess let's just call this our reference angle now. So now if I take this blue angle is going to be our second solution. If I take, let's see, if I do 180 degrees plus this reference angle, that should be my second solution. All right, so my second solution here, this one right here, my second solution will be 180 degrees. Well, I guess it's approximately, because we have an approximation for our reference angle, plus 56.7 degrees, which is 136.7 degrees. Now, the idea being if I do tangent, all right, let's check that. If I do tangent of 136.7 degrees, that should be about 1.5214. So let's check that. If I do tangent, again, we're still in degree mode, 136.7. That gives me, something went wrong here. Oh, I added wrong. It's 236. Why didn't you guys catch me? 236. All right. Let's use our previous entry. Oh, I don't know how to use this calculator. Let's just do it from scratch. Tangent of 236.7. There we go. It's not exactly right because remember we have an approximation here. It's not exactly 1.5214 because we're using an approximation, but it does get us back to close to what we thought it was supposed to be. Now we had some rules before about what the sine inverse button on our calculator does. Tangent, tan inverse of a number. I'm going to go ahead and erase some of this so I have some more room. Tan inverse of x gives the angle in the open interval minus 90 degrees to 90 degrees, which is the same as the open interval minus pi over 2 to pi over 2. Remember, tangent is not defined at 90 degrees or pi over 2. The angle theta with tangent of theta equal to x. And again, why it picks that interval instead of a different interval, we'll talk more about that later on when we have we spend an entire section talking about inverse trig functions. It'll be half of a class period for us. For part C here, a cosine of theta is 1.5214. If we just jump right in and say, well, all right, the calculator answer should be the cosine inverse of 1.5214. Let's see what the calculator says there. Second function cosine of 1.5214. And the calculator says domain error. So apparently 1.5214 is not in the domain of the cosine inverse function. Let's see why. If we had been diligent, as we have been in other problems about thinking about the graph of cosine. So we're still in degrees here. So 90 degrees, 180, 270, and 360. We start at 1 and then go down to 0, then go down to -1, back up to 0, and back up to 1, and then sketch in our curve here. All right, there's the graph of cosine on the interval 0 to 360 degrees. 1.5214 is up here somewhere. Boom. The graph never touches 1.5214. So remember, the range of cosine is, we talked about this last night, -1 to 1. And if you remember some things about the correspondence between ranges and domains for functions and their inverse, the domain of the cosine inverse function, inverse cosine, is the same as the range of the cosine function. Okay? So that's why 1.5214 is not in the domain of cosine inverse. It's actually not in the range. Cosine of theta can never be bigger than 1. Okay, so there are no solutions. I guess technically there are. If we were to have to answer this, there'd be no solutions. We can do, however, we can't do cosine is equal to 1.5214, but we can do secant. Remember, secant, the range of secant, the range here for secant and cosecant is minus infinity to minus 1 union 1 to infinity. And this number's in that interval. Okay? So we're good to go with secant. However, there's no secant inverse button on the calculator. Right, there is a secant inverse function, but it's just not a button that we have on our calculator, just like there's no secant button on the calculator. All right? And just like you would use the cosine button, 1 over cosine, to compute secant on your calculator, we're going to go ahead and have to go through the cosine here. So cosine of theta is 1 over secant of theta. That's a reciprocal identity. In this case, 1 over 1.5214. And then, well, I guess let's just, we've been doing graphing stuff, so let's just look and see that there are going to be solutions and try to figure out where they're going to be. Let's see, secant is going to have asymptotes where cosine was 0, and if you rewind the video or look at whatever graph you have sit in front of you for the cosine function, the cosine function has zeros at 90 degrees and 270, and then here's 1 and minus 1, and the graph of y equals secant of x looks something like this on the interval 0 to 2 pi. And here, okay, now if I go up to y is equal to 1.5214, we see once again that there is a solution in the first quadrant and a solution in the fourth quadrant. All right, so when we hit the solution in the first quadrant is once again going to be the number that the calculator spits out when I do cosine inverse of 1 over 1.5214. All right, so let's do that now. One cosine inverse. I'm getting a little bit of lag here. Clear, 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 clear. All right. Cosine inverse of 1 divided by... I don't like that the fact that this calculator uses a division button. Nobody writes math with a division button past 3rd or 4th grade. I don't think. I don't know. Anyways, cosine inverse is going to be, as expected, a number in the first quadrant between 0 and 90 degrees. So this would be about 48.9 degrees. That's also our first solution, and it's going to be our reference angle. So all of our examples so far, we've had our first solution happens to be the number that the calculator spits out, and that's also the reference angle that we're going to need to find the second answer. Thinking about our unit circle. I'm not even sure why I needed to draw the actual circle. Yeah, there's no need to draw the actual circle. Okay, we got one angle let's see, 48.9 is just a little bit more than halfway through. There's our theta sub 1, which is also the number that the calculator spit out, as well as the reference angle that we need. And then there's going to be, I guess we went this way to get to that angle. And then there's going to be a second angle in the fourth quadrant. At least did a halfway decent job of getting one in where the second angle was in each quadrant. That's going to be our second solution here. Our second solution over here. Right there. And the reference angle for that angle is the same as the reference angle for our first solution. Okay? So here, if I take my second solution and add the reference angle, I should get 360 degrees. So my second solution on the interval 0 to 2 pi is going to be 360 degrees minus the 48.9 degrees, 360. Here I will use the answer button, minus the previous answer is about 311.1 degrees. Okay, so those are my two solutions. These are my two solutions, rounded to the nearest tenth of a degree. Okay. Looking now at problem number 5, which is a similar problem, but instead of working with degrees, we're going to work with radians. Hope I picked some. Yeah, I picked some good ones. Well, let's just practice with some negative numbers. So I'm going to go ahead and make this negative, this first one negative, so that we can work with negative numbers. All right. So, all right, instead of looking at a graph, let's think about this for a second. Oh, I forgot to mention. Sorry. Cosine, the inverse cosine function. I forgot to mention that down here. It says it on your notes. Cosine inverse x gives an angle theta. And now here it's 0 degrees to 180 degrees, or 0 to pi if we're working with radians, with cosine of theta equals x. So that's the new thing about the inverse cosine function is, I guess, the range of the inverse cosine function is different than the range for the inverse tangent function and inverse sine function. These are ranges. These are ranges for those inverse functions. So here we're looking for angles in 0 to 2 pi that satisfy the equation. Remembering that cosine is negative in the second quadrant and third quadrant. That's going to be important for us. In the second quadrant and the third quadrant, that's where cosine is negative. So that's where we're expecting to find our solutions. Now, if I'm not going to drag the page down there again, but the range of the inverse cosine function is actually going to give us one of those. Okay? So let's think about, rather than drawing the graph, let's just look at, I guess, our unit circle without the circle, where that's not 2, that's y. There's going to be one angle in the second quadrant and one angle in the third quadrant. So we will call these angles theta 1 and theta 2. And both of these angles are attained by starting in standard position and going in a counterclockwise direction. Notice that both of these angles are going to have the same reference angle. All right. And we're going to use our calculator answer to figure out what the reference angle is. So, going to the calculator answer. We want to do theta sub 0, that's our calculator answer, is going to get produced by doing cosine inverse of negative 0.9235. So anyways, the purpose for the graphs on the previous problems is to make sure that, to remind ourselves what the ranges were for tangent and sine and cosine. And also to help you visualize where the answers might be, if that's helpful for you. I like the all students take calculus version better to say, oh, okay, I'm going to have an answer in the second and third quadrants because that's where cosine is negative. So anyways, when I do cosine inverse of negative 0.9235. Oh, I forgot to switch to radian mode. See, I'm still in degree mode. We're looking for something in radians. All right, so I got to switch to radian mode. Mode and radians. Enter. Okay. So let's try that again. There we go. Okay, so we want an angle to the nearest, is that at 1 millionth? We got tens, hundreds, thousandths, 10,000ths. That's to the 10,000ths place. So this is about 2.7479 radians. And that's what we expected. That's between pi over 2 and pi. If we think about pi as being about 3, then pi over 2 is 1.5. And so our number should be between 1.5 and 3. So that is actually the angle in the first quadrant that we're looking for. All right, so the calculator answer happens to be the first solution that we're looking for. Now our reference angle, here's where we're going to have to do some work to find a reference angle. Our reference angle in this case, if I take this first answer and add the reference angle, I should get pi. So my reference angle is going to be pi minus my previous answer. So let's go ahead and do that on the calculator. If I do pi minus the previous answer, so my reference angle, now remember all reference angles are in the first quadrant. All reference angles are in the first quadrant. I guess when you put them in standard position, the way these reference angles as they're labeled over here are not in standard position. When you put a reference angle in standard position, it's in the first quadrant. So this is about 0.3937. And then looking at my second solution, if I take a half rotation and then add my reference angle, I'll be at the second solution. Okay, if I go around a half a rotation and then do my reference angle again, I'll be at theta sub 2. And so that's what I will do. I will take this previous answer on the calculator, that's my reference angle, and add pi to it to get the second solution is about 3.5353 when I round to the nearest to 4 decimal places. All right, so here are my 2 answers. All right, those are the angles in 0 to 2 pi that satisfy that equation. So if I go here again, if I apply cosine to my previous answer, see, I haven't done any rounding on the calculator. So if I apply cosine to this answer, we should get something very, very close, if not exactly negative. Yeah, there we go, exactly. So that was a lot of work. For the record, this business of working with inverse trig functions on your calculator, this is not memorize a bazillion different permutations of how this works. This is understand the answer that your calculator produces and understand how to use the calculator answer to find the answers that you're interested in. All right, moving on to the last one in this batch. Cotangent of theta is negative 2.731. There's no inverse cotangent button, so we're going to go ahead and use the reciprocal identity to say that tangent of theta is 1 over negative 2.731. Now we know that tangent is negative in the 3rd and 4th quadrants. And so we're going to have, sorry, the 2nd and 4th quadrants. We're going to have one of our answers, theta 1, is going to be in the 2nd quadrant, and the other answer, theta 2, is going to be in the 4th quadrant. They're going to have the same reference angle, theta sub r. All right, now our calculator answer, when we do theta sub 0, that's our calculator answer. Maybe I should call that theta sub c or something. I don't know. Maybe next time I teach this, I'll call it theta sub c for calculator answer. Will be the inverse tangent of 1 over negative 2.731. One divided by negative 2.731, which is a negative angle. All right, so here we go, guys. This is one where we actually have 4 different angles. 3, 5, 1, 0 when I round to 4 decimal places. So anyways, this reference angle is going forward, not backwards. This reference angle is also going forward that way. Our reference angle, when I put it in standard position, is right here. And our calculator answer, I guess I got to draw that in green now, is going backwards into the 4th quadrant, theta sub 0. All right, now finding our reference angle, that's easy enough. Our reference angle is negative, the calculator answer, all right. For our first angle that we need here, theta sub 1, if I take theta sub 1, so let's go ahead and turn our calculator answer into a reference angle. There we go. Now we have a reference angle on our calculator. For the first angle that I want, if I take the first angle, theta 1, and add the reference angle, I get to pi. So I can find my first solution by taking pi minus the reference angle. So I will go ahead and do that on the calculator. Take pi minus the reference angle that was the previous answer. All right. So that's about 2.7906. Now to get the reference angle back, I'll let you go ahead and oh God, the lag is crazy. Take pi minus, there we go. Now we got the reference angle back on the calculator. For the second answer, if I take my theta sub 2 and add the reference angle, I should get 2 pi. So the second answer, select the second answer that they want for this problem will be 2 pi minus my reference angle. So I will do that on the calculator. 2 pi minus the reference angle that was the previous answer gives about 5.9322 when you round to the 4th decimal place. All right, so this topic is one of the ones that's historically the most confusing in this class. Okay, we saw in this last example there's really 4 angles. The way that I think about these problems, there's really 4 angles going on. All right, so if you can devise a better way of understanding the problem and a better procedure that works for you, be my guest. But this is what works for me, and this is how I think about the problems. Again, it doesn't. We talked about finding formulas for reference angles and things in class, and I don't think memorizing formulas is the way to go here. It's understanding the ideas, understanding what your calculator's doing. Maybe you don't have to understand why your calculator is doing what it's doing. You don't have to understand what's going on inside the calculator, but understand what the answer that your calculator produces, what that answer means, and how it's relevant. And then also understand how to use that answer. Okay, let's look at a couple of the problems that we skipped over last night. We're going to go through these very quickly. We don't need the calculator anymore. We did some stuff like this in the context of other problems last night. So in 4 here, we want to use the formula for negatives to find the exact value for each of these expressions. Sine of negative 3 pi over 2. Remember, one of the formulas for negatives is that sine of negative x is negative sine of x. I don't need that parenthesis there. So sine of negative 3 pi over 2 is negative sine of 3 pi over 2. And then if you look on your unit circle, sine of 3 pi over 2 is, I just lost it myself. Oh, sine of 3 pi over 2 is 3/4 turns around. Right? We go here, there's 1/4 turn, and then another 1/4 turn, and then another 1/4 turn. There's 3 pi over 2. And sine is the y coordinate of that. So sine of 3 pi over 2 is negative 1. So that would be positive 1. Cosine of negative 225. That would be negative cosine of 225 degrees. 225 degrees is halfway through the 3rd quadrant. And cosine halfway through the 3rd quadrant is negative root 2 over 2. Again, looking at your unit circle at the start of the next section. See, now that we have that information, there's no reason to use triangles and things to figure all this out. By the way, oops, that's not cosine doesn't do that. I don't know what I was thinking. I lost track. Cosine doesn't do that. Cosine is one of the even functions. Sorry. Got distracted. Cosine of negative x is just the same as cosine of x. Sorry about that. Tangent, on the other hand, tangent's another one of the odd functions. So tangent negative pi over 4 is negative tangent of pi over 4. The minus sign pops out. Oops. I should... I'm losing my mind a little bit here, guys. Sorry. So that's tangent of pi over 4. Pi over 4 is in the first quadrant. It's halfway through the first quadrant. The x and y coordinates halfway through the first quadrant are the same. So tangent of pi over 4 is 1. Or, yeah, you need to look at your unit circle to see that the coordinates are the same. But so when I take the ratio, I get 1. So there's some... the key thing here is applying the formulas for negatives, which I unfortunately didn't do a very good job of. Another thing that we could have done, I'm just going to do these with the first couple, is use the theorem on repeated values. So remember, the sine and cosine are 2 pi periodic, meaning if I add 2 pi to the argument, then the value is still the same. If I go one full rotation around, everything stays the same. So sine of negative 3 pi over 2 plus 2 pi. When I add 2 pi to 3 pi over 2, that should be pi over 2. Thinking about sine of pi over 2 is, all right, gets us to the straight up position. The y coordinate on the unit circle straight up is 1. For the next one, repeated values, we're supposed to, again, add a full rotation. So this would be cosine of negative 225 degrees plus 360 degrees. Let's see, now I need my calculator again. If I do 360 minus 225, that's 135. That's 90 plus 35, so that gets us over into the second quadrant. And I guess if we wanted to use triangles, we'd have our 45 degree right triangle, which we know has side lengths root 2 over 2 and root 2 over 2. But since we're in the second quadrant, the x coordinate is negative, so this would be minus root 2 over 2, which I think that's what we got on the previous one, right? Yeah. Okay. So we did this comparable stuff of using theorems on negatives and adding rotations to make other problems easier in the examples that we did look at last time. Some examples that weren't on our sheet, some verify the identity stuff that I told you guys that we would do in the video here. First off, let's write down the identities that we can use. There are some reciprocal identities. I forgot an I here. Let's see. Cotangent of theta is 1 over tangent of theta. Secant of theta is 1 over cosine of theta. And cosecant of theta is 1 over sine of theta. I think I told you guys, every time you sit down, you should write down all the formulas that you think you're supposed to know. So write these down. If you want to write down, hey, tangent is also the reciprocal of cotangent, that's fine too. I'm not going to do that here. The tangent-cotangent identities would be tangent of theta is sine of theta over cosine of theta. Now, it's not necessarily super important that you know the names of the, like you don't necessarily need to know that these are called reciprocal identities and that these are called the tangent-cotangent identities. But it's helpful. It's helpful to put a name. It helps you to remember which ones you're supposed to know. Anyways, the cotangent identity would be cotangent of theta is cosine of theta over sine of theta. That's the reciprocal of tangent. The Pythagorean identities, the primary one is sine squared theta plus cosine squared theta is equal to 1. The next one would be tangent squared theta plus 1 is equal to secant squared theta. If you get that, you get the second identity by dividing through by cosine squared theta. Take the first one and divide everything by cosine squared theta, and you would get the second one. If you instead divide everything by sine squared theta, you would get 1 plus cotangent squared theta is equal to cosecant squared theta. So those three are the Pythagorean identities. And then last time we learned the formulas for negatives. That would be sine of negative x is negative sine of x. Cosine of negative x is just cosine of x. Tangent of negative x is negative tangent of x. Cotangent of negative x is negative cotangent of x. Secant of negative x is secant of x, so the cosine and the secant are the only two that eat up the minus sign. Everything else lets it through. Cosecant of negative x is negative cosecant of x. So those are the formulas for negatives. These are the ones that we have available to us right now. I told you guys last night that there's going to be lots more identities. I think these are going to be the identities that we need to know. Right now, we got these two, and then we're adding all of these at a later date. Now, you don't necessarily have to have all these memorized. Some of these you could memorize half of them and be able to derive the rest of them. We'll cross that bridge when we get there, but I just wanted to give you guys a visual on, hey, we told you there were going to be a lot of identities. These are the ones that some of you were upset about. Well, upset's maybe a strong word. You were like, hey, do I have to memorize those? I'm like, yeah, you have to memorize those, and there's all the rest of these too. Unfortunately, you guys don't get to use notes and cheat sheets and things like that. Anyways, let's do some verify the identity using those fundamental identities, as well as I guess in one case, the formulas for negatives. In this first problem, and all these we're going to transform the left-hand side and the right-hand side. We don't necessarily have to go that way, but I think that's the way that makes the most sense. We're trying to turn an expression here on the left that involves both cosine terms and sine terms into something that only involves cosine terms. So I somehow have to turn the sine terms into cosine terms, and I can use the Pythagorean identity to do that. All right? So I'm going to start with my left-hand side, cosine squared 2 theta minus sine squared 2 theta. Using the primary Pythagorean identity, the sine squared 2 theta, so let's just write it off here on the side, cosine squared theta plus sine squared theta is equal to 1. So sine squared theta is 1 minus cosine squared theta. And that works for any argument. Argument. One of the things that's a little bit troubling here is we have the argument 2 theta, but the argument doesn't matter. I can turn the sine squared stuff into 1 minus cosine squared of the stuff. Then when I distribute the minus sign, that becomes cosine squared 2 theta minus 1 plus cosine squared 2 theta. And when I combine like terms, I have 2 cosine squared 2 thetas. And that's where we were supposed to stop. So this is the entirety of my solution for this problem. It's a string of inequalities where each stage is separated by basic algebra or a trig identity. On to the next problem. I'm supposed to turn sines into secants. Now here's one. All right, here's one actually where it might be helpful to start from the right. And I guess if I were working backwards, you might recognize 1 over secant theta is the same as 1 over secant theta squared, using some facts about the notation. and properties of exponents. And then 1 over secant is cosine of theta. So I got cosine squared theta. It's like, all right. Now, instead of having to turn the sines and the secants, I just have to turn the sines into cosines. So we kind of worked our way back from the end to maybe give ourselves an easier target to hit. Okay? And now that I see that easier target to hit, I'm more comfortable doing some basic algebra and saying, all right, this is a special product formula. If you take an expression times its conjugate, you guys remember learning about conjugates in algebra? Take an expression times its conjugate, you get the difference of squares. And hey, there's nothing else to do. 1 minus sine squared is the same as cosine squared by a Pythagorean identity. So we got some basic algebra, Pythagorean identity, some reciprocal identities, and we're done. So sometimes you can kind of work to meet in the middle. And sometimes that's an easier task. But here, my solution again starts with the left-hand side is a string of equalities. A is equal to B is equal to C is equal to D is equal to E. And using the transitive property of equality, if A is equal to B and B is equal to C, then A is equal to C. And if A is equal to C and C is equal to D, then A is equal to D. And if A is equal to D and D is equal to E, then A is equal to E like we wanted to. Okay? This was A and this was E, I guess. So there's that one. The next one, 1 minus sine of theta times 1 plus tangent of theta is equal to 1. Well, here, our right-hand side, I don't see anything to do with the right-hand side, so we kind of have to go with the left-hand side. Now, you want to start to recognize some of these Pythagorean identities when they show up. Anytime you see sine squared stuff, you're like, hey, maybe I can use a Pythagorean identity to write that in terms of cosine squared. And so remembering cosine squared theta plus sine squared theta is equal to 1. All right, let's start with my left-hand side. One minus sine squared. If I just subtract sine squared from both sides, that is cosine squared theta. And then the second Pythagorean identity, tangent squared theta plus 1, is equal to secant squared theta. So 1 plus tangent squared theta is secant squared theta. And now we're almost home. Secant squared theta, using a reciprocal identity, is 1 over cosine squared theta. And then using basic algebra, cosine squared times the reciprocal of cosine squared is just 1. I think I got 2 more here. Yeah, 2 or 3 more. Cotangent theta plus tangent theta is cosecant theta plus secant theta. So here's when I'm going to take a slightly different approach. I'm just going to transform my left-hand side into something and transform my right-hand side, hopefully, into the same thing. I mean, that's the goal. So if I write everything in terms of sine and cosine, cotangent theta plus tangent theta is equal to cosine theta over sine theta. Plus sine theta over cosine theta. Now I've got 2 fractions. If I want to multiply them together, I need a common denominator. That common denominator is going to be sine theta times cosine theta. In order to get the cosine theta downstairs, I have to multiply on top by it as well. So I get a cosine squared theta in top in that first fraction. And similarly, we get a sine squared theta in top on the second 1. And when I add these two fractions together, I have cosine squared theta plus sine squared theta is over sine theta cosine theta. And then maybe you don't see where we're supposed to go from there. And so you're like, all right, let me play with the right-hand side and see what I can make out of the right-hand side. Cosecant theta times secant theta. Well, if I want to write everything in terms of sine and cosine like I just did with the left-hand side, that would be 1 over sine theta times 1 over cosine theta. And if I do that fraction multiplication, that's 1 over sine theta cosine theta. And so now I've got two fractions that have the same denominator, and you're trying to say that they're equal, right? We're trying to say that the left-hand side is equal to the right-hand side. And you're like, well, how do I turn cosine squared theta plus sine squared theta into 1? And then you go, oh, duh, that's a Pythagorean identity. Cosine squared plus sine squared is 1 over sine squared theta. Sorry, sine theta cosine theta. All right, so here's another alternative for how to write up a trig identity. Just transform the left-hand side and the right-hand side into the same thing. Okay, here in the last problem, I guess it was 2 problems ago, we identified a middle point target, but we still managed to get it all written in one line. Here, we weren't necessarily able to identify a middle target. We just stumbled across the right middle target. Okay? So here's another alternative for writing up your verify the trig identity solutions. I got 2 more, I guess. 2 more. These are ones that involve the formulas for negatives. If I do cosecant of negative x times cosine of negative x, for cosecant's one of the odd functions. It allows the minus sign to pass through. And cosine is one of the even functions that eats up the minus sign. Now my target is cotangent. So here's another problem where it can be beneficial to say, all right, if I were going to try to play with the right-hand side, I would use a cotangent identity to write it as cosine x over sine x. And that might be the motivation to write everything in terms of sine and cosine here. So cosecant is 1 over sine. That's a reciprocal identity. And hey, there's nothing else to do. When I do basic multiplication, I get negative cosine over sine. All right, so there's a good answer for that one. And then this last one. Looking at the end point is once again negative cosecant, so we can know in our heads that we're heading for 1 over sine, probably. And we can start by transforming things to be in terms of sine. Now, before we do that, let's go ahead and apply some formulas for negatives to our left-hand side. Cotangent is another odd function. It allows the minus sign to pop out. Cosine, as we've said a couple times, is an even function. And sine is an odd function, so the minus sign pops out there and becomes minus sine of x. So we're using formulas for negatives there. Now when I use the cotangent identity, cotangent of x is cosine over sine. When I do some algebra on that first term, I get negative cosine squared x all over sine x. And then if I want to add these two fractions together, I'm going to need to write the second business as a fraction over sine of x, which means I need to multiply on top and bottom by sine of x. And so that becomes sine squared x. If you factor out a minus sign, this becomes cosine squared x over sine x plus sine squared x over sine x. When I combine those fractions together into one fraction, since they have the same denominator, I get cosine squared x plus sine squared x. And then, all right, we hopefully are starting to figure out now that cosine squared plus sine squared is 1. That's a Pythagorean identity. 1 over sine of x. And that's where we were, oops, we got one more line. That is negative cosecant of x. That's where we were supposed to end. Okay? Now, I've said it many times, these verify the identity problems, they are primarily about getting comfortable working with the identities. And so when you're stuck somewhere, pull up that list of identities and see which identities you can use and manipulate the expressions. Okay? Don't break any algebra rules in the process, but don't force anything to happen. Just do stuff and see what happens. Okay? That's all I have for this video. If anybody has any questions about this, please email me or message me on IvyLearn or send me an Ask Your Teacher message on WebAssign. And if I don't hear from you before then, I'll see you all on Wednesday.